we're given this question where we want to find the expected value of a function of a continuous random variable. We're given the PDF of y, and then we're told that w is a function of y, and we're given the PDF for w. And we're asked to find expected value of w in two different ways. Let's look at what these two different ways are. So approach one is going to be use PDF of W, which is given, right? You're already given the PDF of W. We can use it to find the expected value W, like we'd find the expected value of any continuous random variable. We know how do we find the expected value of any continuous random variable using its PDF? We integrate from minus infinity to infinity W times its PDF, which is FWW. So we're going to do this integral. This is how we find the expected value of any continuous random variable given its PDF. So now we can write this as an integral from 0 to 1 w 1 by under root w, right? Because this is only with PDF is non-zero. So we restrict so in general, the integral is minus infinity to infinity, but in this case, we reduce it over the universe 0 to 1, which PDF is non-zero, right? I'm sorry. So PDF is only non-zero from 0 to 1. So now we just simplify this a little bit to do the integral. So when I simplify this, oh sorry, my bad. The PDF was 1 by square root w minus this was this is right. The PDF is 1 by square root w minus 1. So now we just simplify this a bit, and you can simplify this by writing it like this: w minus 1 by 2 minus 1 dw. Now I'll just multiply we'll just expand this. So by multiplying w minus 1 by 2. So when you multiply like basis, powers get added. So this becomes w 1 by 2 minus w, and this becomes dw. So now we just need to do this integration. So this integration would just be w 1 by 2 plus 1 by 1 by 2 plus 1 minus w squared by 2. How are we doing this? Let's just recall for this. Recall that whenever you integrate xa, the integral of that is xa plus 1 divided by a plus 1. So here, when you're integrating w power 1 by 2, it's w power 1 by 2 plus 1 by 1 by 2 plus 1. Then it's minus w power 1 plus 1 divided by w divided by 1 plus 1. Right? And then what you do is just plug in the limits inside this. Or if you just simplify this a bit, this becomes w 3 by 2 divided by 3 by 2 minus w squared by 2, 0, 1. So now when I plug in the limits inside this will become 1 by 3 by 2 minus 1 by 2, and you can simplify this, and this turns out to be 1 by 6. So approach 1 was that you can find the expected value w using its PDF, which is given to you. And we know how to find expected value for any continuous random variable. We did it like this. Now there's another way you can actually find expected value w. What is approach 2 here? Use PDF of y. Instead of using PDF for w, use PDF of y, which w is a function of. Which w is a function of. Because w is given to us as a y square, right? So we can use PDF of y. Why does this work? Because recall expected value of a function of a continuous random variable, in this case gy, is just going to be the integral from minus infinity to infinity gy fy by dy, right? So if you want to find the expected value of a continuous random variable as itself, we do expected value y is minus infinity to infinity y times PDF of y. You integrate this thing with respect to y. But if you want to find using the expected value for function of a continuous random variable, in this case a function of y, which is w, so you can still find it, right, using the PDF of y, right, of which w is a function, because then you can say expected value gy is minus infinity to infinity gy, right? In this case, gy is equal to y square, which is w. We want to find the expected value w, right? So expected value w is just the expected value of y square, because w is equal to y square. And then we can use the PDF of y as y square fyy dy. Right? So gy here is, like we know, gy here is y square. Right, and now we can again write this integral, rewrite this. In general, the integral is from minus infinity to infinity, but we can write it over those values where the PDF is non-zero. So we have y squared and we have the PDF of y, which is 2, 1 minus y dy. Right, this is because PDF is only non-zero. So PDF of y is only non-zero from 0 to 1. So PDF of y is only non-zero from 0 to 1. Right, so we can rewrite the integral from minus infinity to infinity, the integral where the PDF is non-zero. So now if we just simplify this integral a bit, we can take the 2 out. And we can just expand this by multiplying this y star with 1 and y. So this becomes just y star minus y cubed dy. And when you want to do this integral, we'll do it similar to how we did the integral of w. So this would be y cubed by 3. So we have a 2 here minus y4 by 4, 0, 1, right? So let me just clear this up. So we're writing our integral. So we said it is 2 y3 by 3 minus y4 by 4. Again, this works because you want to recall the integral of x power a is xa plus 1 by a plus 1. Right, so we're just using this integral rule here. And I'll just plug in the limits. So this just becomes 2, 1 by 3 minus 1 by 4, which is going to be 1 by 6. So I found the expected value W using two approaches. One, if you know the PDF W, just use that. Even if you don't know the PDF of W, we could find expected value W using the PDF of Y, of which W is a function of. So the key takeaway over here is that using approach 2, where we use the PDF of Y, which W is a function of, you don't need to know the PDF of W. Need to know You don't need to know the PDF of GY, which is W in this case, function of random variable. So you don't need the PDF of the function of the random variable to find its expected value. All you need is PDF of Y. Find its expected value. All you need is PDF of Y. So even if we did not know the PDF of W, in this case, this was not given to us, we could still find the PDF of W, which is y square, using the PDF of y like we did in approach 2. So to find expected value function random variable, you don't need to know the PDF of that function, you just need to know the PDF of the random variable, because then we can find expected value of gy, we know as the integral from minus infinity to infinity gy f y, right? So whenever you're finding the PDF of a function random variable, you don't even need to know this, right? If as long as you have the PDF of the random variable or which it is a function of, you can easily find its expected value.